Alright, I'm really sorry about that. I did not see that one coming. I need to watch the clock better so I can stop these things in between problem numbers. Alright, so we were about to do 5 little trials to see if, see which ones of these little strings of 5 random numbers produce 5 in a row trains on time. So, I was about to say this was all on time, but it's not because there's a 7 in it, so it's not all on time. I'm looking for, is there a 7, 8, or 9? And if there's a 7, 8, or 9, then there's some late trains. So there's a bunch of late trains. There's a bunch of late trains. This one has some late trains. This one has some late trains because there's 7s, 8s, or 9s in all of these. Here's one that doesn't have any 7s, or 8s, or 9s. So all those trains are on time. There's a late 9, there's a late 8, there's a late 7, a late 9, and some 9s, there's some 9s, there's some 9s, there's some 8s, there's some 8s, there's some 9s, there's, okay, here we go, those are all on time. There's a 9 in there, this is all on time. There's some 8s in there. This is all on time. Good. There's a 9 in there. This is all on time. That's good. They're getting better. That one's got some late ones, and that one's got some late ones. So out of my 25 trials, how many were all on time? 1, 2, 3, 4, 5. 5 out of 25, or 1/5 of the time. 1/5 of the time, by time I mean the times when we picked 5 trains in a row. One at like 20% of the time, all 5 of them are going to be on time. Yeah, I think this answers the question. And this doesn't really answer the theoretical probability question of, okay, if it's a 70% chance all the time, what is the actual probability that there's 5 in a row on time? That would be 0.7 to the 5th power. I have no idea if that's close to this. Probably must be somewhat close to that. You know what? I'm curious. Let's just find that out. Again, this is not the question. I'm just asking this. What would happen if we took 0.7 to the 5th power? Are we anywhere close to 20%? Yeah, we're kind of close to 20%. It's like 17%. But that's not what this question is asking. This question is asking, well, let's actually do this. Let's use this random number chart as a way to sort of roll the dice here and see how many turn up. Okay, this one seems like a really random question, and it's not something we spend a lot of time talking about in class, and it's really very open-ended. Explain how to use technology to estimate this area. The graph of tangent, I've already put on this calculator over here. The graph of tangent looks like this. Let me sketch it quickly on this page for you. Okay, so here's the graph of tangent from 0 to pi over 4. Well, pi over 2 is where tangent goes crazy and goes up to infinity, and there's sort of an asymptote here, so it never really gets there. But at pi over 4, it crosses that, right? That's actually where that's where we're talking about 45-degree angles, and that's where the tangent is 1. That's where the slope is 1. But before that, if you look at this again, before that it kind of swoops up like this. So there's kind of this kind of thing going on, and it goes up and it goes crazy over there, and then there's some behavior over here. We are really talking about, though, let's estimate this area. The area under that curve. This is starting to sound a lot like calculus, by the way. You're talking about areas under curves all the time. How could we estimate this little area here from pi over 4 to 0? It's kind of a triangle shape. How could you estimate that area using technology? And of course, this is in the probability chapter, so that's fine. One way to do that, let me just explain one. You might come up with another way. You could do a number of different things, but basically we're trying to compute this area with probability and some sort of simulation with technology. I was thinking, okay, basically make the computer a dartboard where this is pi over 4, this is 0, this is sort of the boundary of this square, this is 1, and this is the coordinate pi over 4 comma 1. And you know you have this little curvy kind of thing in here. We're trying to find this area. Pretend this is like a dartboard basically, and you're going to tell the computer, okay, generate me a random set of coordinates x comma y, where both these things are random, and do that, you know, a million times, and you would restrict x. Remember, like you're allowed to do whatever you want here in this technology simulation. Like you can make up all the stuff you want. I'm thinking, okay, tell the computer, pick a random x between 0 and pi over 4. Maybe you can tell by the tone of my explanation of this thing that this does not seem very test-like. And y has to be between 0 and 1. So pick me a random set of coordinates computer that's between here and here. Basically, that has to be in this square. Then we could tell the computer to tell us how often did it fall in the yellow zone, how often did it fall in the white zone, and we would get this huge fraction of white over. Actually, no, I don't want white over anything. Yellow is the favorable area. I have yellow. I don't mean y. I mean yellow over total square. You know, of total, maybe not total square, but total number of trials that it happened. I'll just say total. Now, out of the total number of times that, you know, the thing was thrown, I'm saying throwing darts, like virtually throwing darts, like picking random the computer's picking all these random points in here, and then it's just going to count when it does that. How often did it hit one in the yellow zone? How often did it hit one in the white zone? I want yellow divided by total, and that will kind of give me an idea of what percentage of this box's area that we have here. Oh, and what is the area of this box? The area of this box would be pi over 4 times 1. So that, just to convert it to an area unit, I multiply it by the area of the box. But that's kind of out there. Another technology simulation you could make. Oh, I don't know. I can't really think of one that wouldn't rely somehow on technology generating random numbers, because that's really all technology can do for us in terms of probability simulation. Even like that last question where we had the train. It was all about random numbers and how to turn the random number generator into something we can convert into a probability situation to meet our needs. So this is probably the best one, I would venture to say. Of course, you could actually, this isn't really technology, but you could actually build a dartboard, graph this thing on here, and throw darts all day and just keep tally marks. This is a whole lot faster if you have a computer do it. You could do this with Microsoft Excel. You could do this with your TI-84. It would take a long time to actually write in all this code and do it correctly and have it run a bunch of simulations. But that's basically the computer science theory behind what would actually be going on here. All right, number 16 here is actually the last question on what they are calling a chapter test. The next page after this in your little review packet there is actually a different form of the test. So by here you're supposed to have covered everything on the test, everything in the chapter. And the last thing in the chapter, of course, was probability distributions. Verify that the table below could possibly even be a probability distribution. Well, I don't know what X represents. It represents some sort of outcome that could have 6 different possibilities, like maybe rolling an unfair die. I have no idea. And they're telling us the probability that's going to come out of 1 is about 5%. And about 7.5% for 2, and etc. Well, if this is supposed to be a probability distribution, first of all, the first main requirement, actually the only requirement, is that all 5 of these things have to add up to 1. Can I do that and not overlap this too bad? I can move it over here. You can't see it as you can't see the whole thing, but oh, maybe it'll be fine. Okay, get out of that. And here, let's do this. Okay, so I need 0.05 plus keyboard 0.075 plus what happened there? 0.05 plus, oh, that's weird. I'm using a new system here. This thing is a lot faster than the old one though. I'll leave off that 0. Plus 0.275 plus 0.4 plus another 5%. And I get, survey says, 1. That's great. Okay, so I'll just say this. Yes. Adds. I could probably type this on here. That might be easier to read and faster. Yeah, so that's a probability distribution. What's the expected value of the distribution? Okay, I'm going to do this. You don't have to do it this way, but I'm going to show you a picture of what I'm doing so you can kind of know what's going on here. This is like the dice sums. You had all the different possibilities here. This is like the axis is going to represent the probability of X for each one of those things, and this is the axis for X. And the highest one I need to worry about, I guess, here is like a 0.4. The highest probability anything has is a 5. That goes up to 0.4. The 6 and the 1 are really low. That's 5%. 2 is a little bit higher, 7.5%. 3 is double of 2, and 4 is even more than that. So it kind of looks like this, if you were to make a picture of that. And really what we're getting at here is what's kind of the average of all these. And there's this, you can kind of think of it as there's this many 1s, and there's this many 2s, and there's this many 3s, and there's this many 4s, and there's a whole bunch of 5s. And there's hardly any 6s. And so what's going to be the average of all the different outcomes? Well, 5 is going to weigh into that the most because it's got the most here. 6 is going to add to the average number because there is a possibility that we get a 6. There's an expectation that, yeah, 6 does add to the mean of all the different outcomes, just not very much. So that's sort of a long explanation of why this is what we do. All right, so the expected, oh, and let's use the cool Greek letter, mu equals 1 times the possibility that 1 happens plus 2 times the possibility that 2 happens. Now that doesn't mean I'm like doubling the probability that 2 is going to happen. I'm just counting it double because 2 is worth more than 1 in the grand average of possible, and I like to call this unfair die. 2 counts double in terms of what this expected number is going to be. So it needs to pull it up harder than a 1 does. Okay, times 3 plus the possibility that that 3 is going to happen, plus 4 times the probability that it happens, plus 5 times the probability that it happens. This is really fun to watch. Plus 6 times the probability that it happens. See, so this 6 does add to the average. I mean, because there are some 6s happening there. They just don't happen very often, so they don't get to add much to the average. The 5 adds a lot to the average because it happens so much, and it is such a large number. Okay, I am going to type this into the calculator, but I'm not going to make you watch that. It's like watching paint dry. This was part of that previous thing. Okay, be right back. All right, so I typed all that stuff into the calculator, and I got 4.05. That means, and this is kind of nice because it's a little bit lopsided compared to all those obvious examples we were getting before, that the average we should expect to get this on this unfair die roll is we should, on average, get about 4.05 as our result. Now, 4.05 isn't really a choice. You can roll a 4 or you can roll a 5, assuming this is really a dice thing. But on average, if you rolled the dice over and over again and just took the average of all the results you would get, we would expect over time the average to approach 4.05. I have a few more minutes left in this video, so I'm going to go ahead and go on to the next page of your little document there. It's about rolling 2 octahedral die, which, I don't know about you, those are my favorite size fair dice. Anyway, they are labeled 1 through 8, just like you'd expect, so just like regular dice, except for they go up to 8. Describe an experiment related to 2 dice and list the sample space. Well, you know what? Let's do the sums, like we did before. First of all, how many ways is this going to turn out? Well, it's just like rolling 6 6-sider and a 6-sider, which was 6 times 6, making 36. But here I got 8 possibilities and 8 possibilities, so guess what? There's going to be 64. Let me make that sample space. And wave the magic wand, and poof, there it is. There's all the possibilities for rolling 2 8-sided dice. And let's say, okay, so describe an experiment related to the 2 dice and list the sample space. Well, here's the sample space. Then describe 4 events, E sub 1, E sub 2, E sub 3, E sub 4, that satisfy these conditions. Okay, I think we want to start doing sums because that's going to be the most, this would be the thing you have the most experience with. And the sums would go, of course, from 2, 3, 4, 5, 9 is the most popular sum. It's the longest diagonal, all the way up to 16. We need to have one event, describe one event that's impossible, describe another event that's going to happen half the time, another event that's always going to happen, and some event that happens between a half the time and all the time. E1, oh gosh, I'm going to run out of room now, aren't I? I took up all the room with my sample space. Let's move this a little bit, and then I think I can get some of that stuff over here. Okay, leave myself some room over here. Event 1, let's say that has to be, still not, I don't have much room, do I? Probability that something is going to be like not going to happen at all. Let's say the probability that you roll a 9 at all. I don't mean sum of 9. Actually, you know what? We're talking about sums, aren't we? Let's say some other crazy sum. Let's say the probability that the sum equals 17. Absolutely crazy talk, because the biggest sum you can ever get is 16. E2, probability something happens half the time. Oh, I don't know, something that happens half the time in here. You might say something like, well, there's sort of a cheater one you could use here and say, like, okay, I say the first die has to be even. Well, that's going to happen half the time. Or the second die has to be odd, or something like that. But if we really are going to talk about sums, you got to be a little more creative. Let's say we got to highlight half these sums somehow. I think that one on the regular dice, if you do odd sums or something like that, it turns out to be half. So if we did all the odd sums, that's odd, that's odd, that's odd, it's kind of hard, that's odd, that's odd, and that's odd. And if I count all those up, I'm pretty sure it would be half. Yeah, I just took a little break there and counted up all those stripes, and sure enough, there's 32 highlighted things there. So we'll say sum is odd. Okay, what's the probability that of something that's always going to happen? You might say something like that the sum is, well, this sounds silly no matter what you do because it's about the sum, it's about something always happen. Say the sum is, I don't know, greater than 1. Fine, all these sums are greater than 1. That's a sum of 2, and we go all the way up to 16. So any old silly event that you are sure has to happen will have a probability that equals 1. And E4, a probability is between half and between half and all. Let me get rid of my highlight marks first. Well, really for that, all we need is say like the sum has to be greater than something. The sum has to be less than something. This is the probability that it's 9. If we pick 9 and everything above that, that would be more than half right there. Or just to be safe, let's say, oh, just to make sure we really do have more than half, let's say 8 and anything bigger. I have a few seconds left to say sum is greater than 8. Okay, thank you very much.